All right, so in this section, we're really going to tie up any loose ends about finding the area under a curve using these rectangles. In the last section, we talked about a finite sum being an approximation. Now we're going to introduce the idea of a limit along with it, allowing us to now have infinitely many rectangles and get an actual area. Now, again, this is a big summation type of chapter. You saw that in the pre-chapter work. And there's a few things that we need to address before getting into the actual area idea. So if you're a little rusty on your summation rules, please review those, page 260 in the text. The summation formulas that I have up here, they're formulas that we're going to have to use here in a little bit, but I just wanted to present them to you now. We'll look at an example on kind of how they'll work with us, but those are also in your text. But more importantly, the proofs of them are in Appendix 2. These are actually proofs by mathematical induction, which is one of the easiest forms. So I would really encourage you to go to Appendix 2 to look at these proofs. I don't necessarily think that they're obvious. These statements are obvious. So seeing the proof and better understanding where they come from might help you remember them for the future. So anyway, those are the summation formulas. We're going to take a look at an example here using them where they give us a sum from k equals 1 to 7 of k times 2k plus 1. So we want to be able to now take this thing and rewrite it into stuff that looks like this, then noting that our n is equal to 7. Okay, so to do this, what I would do is first distribute the k, and then actually distribute the sum. So that's going to be the sum from k equals 1 to 7 of 2k squared plus the sum from k equals 1 to 7 of just k. One of the other properties states that we can take this constant and pull it outside of the sum. So the 2 could come out, leaving us with the sum k equals 1 to 7 of k squared, and then plus the same thing but with just a k. Now, we've hit this formula right here would be our k squared, and this formula for this guy would be our k right here. So I'll take this now, and my formula says for k squared, n times n plus 1 times 2n plus 1 all over 6. But again, now we're noting that our n needs to be evaluated at 7. And then plus the formula for just the k to the first. And that's also evaluated at 7. So when you do that, when all's said and done, you've plugged the 7 in for all these n's here and here, and then you evaluate. Again, that's just some number crunching. I'm not going to spend a lot of time on the video doing that. You get 308. So this sum right here that we started with, all 7 terms when added together give us 308. But we were able to avoid the monotony of the number crunching by simply taking advantage of these summation formulas that we'll need here in the near future. Okay, so now we're ready to talk about this huge idea of the limit definition for area, also sometimes referred in context as the Riemann Sum. Now, the picture that I started you out with is a pretty standard picture, and we're going to build this thing up using some of the techniques from the last section as well. Now, I've put together these rectangles very, very inconsistently on purpose, so don't judge that. Don't think anything different of that. I've been very inconsistent with those rectangles intentionally. So what I'm going to do first is I'm going to go ahead and just do some labeling. We're going to call these x values starting at A, x0, x1, x2, all the way up to B, which is x sub n. Okay? Now, that's also going to give me an opportunity to name some of them generically. So maybe right here, if we call this guy x sub k, then the one previous to it would be x sub k minus 1. Okay, so you can see instead of using specific numbers all the way through in a general form, if that's x sub k, that would be our x sub k minus 1, and these would be somewhere between 0 and n. Okay, now let me go ahead and outline the process here that we're going to embark on. The first thing that we're going to do is something that I've already kind of done. we're going to divide our region being this guy right here, the region that we want to find the area of. We're going to divide the region into n equal with subintervals. So we divided the region into n equal with subintervals. And remember, I was pretty crazy with how I constructed these rectangles, but I do want them to be equaled with. Okay, so on the bottom here, these should all be about the same equal width for now. Now, since they're equaled with, the width can actually be computed using how we've labeled things as b minus a over n. So this number minus this number divided by the n number of subintervals, just like we did in the last section. All right, step 2 is we're going to let x0, x1, x2, all the way through x sub n be arbitrary points in the subinterval. So the x values are arbitrary points in the subintervals. We're going to talk more about this arbitrary points thing in the next slide, but for now they're just arbitrary points somewhere in these subintervals. So maybe one's here, maybe one's here, maybe one's here. Doesn't matter. Just arbitrary points in the subintervals. Again, that's why I'm a little bit off up here, as long as we're equaled with down here. All right, so if those are arbitrary points in the subintervals, then f of x0, f of x1, f of x2, all the way to f of xn are heights of the rectangles, just like they were in the last section. So those arbitrary x values are going to map to our heights, allowing us to hopefully then find the area. All right, so then for now, step three. We're going to start talking about actual area now that we've got heights and widths taken care of in steps 1 and 2. So the area of a rectangle is going to be base times height. So the area for us now is going to be a base right here, right here, right here. Remember, they're all equaled with, though, a base of what we're going to call delta x. So here's our base, delta x. Our heights were these guys right here, and so for our height, we're going to use the arbitrary f of x sub k. And then we also now know we want to add up all of them. So that's where our sum is going to come in. The sum is going to be from k equals 1 to n, since there are n of these rectangles. So now using our summation notation, we've got our base, our height, and we've got n of them now we're adding up. Now, the last step, this is where we really take it all the way. As n goes to positive infinity, right? That's the only way to get an actual area, is for there to be infinitely many rectangles. As n goes to positive infinity, we need to introduce the limit. So the area is going to be the limit as n goes to positive infinity of the sum from k equals 1 to n of f of x sub k times delta x. So this guy right here, that's our limit definition of area. Now, this is a very, very intuitive idea. There's really nothing complicated about it. You just have a bunch of rectangles, you find the area, and you add them all up. Now, there have been some concessions made in doing this. For example, one of them being that we divided into equal subintervals, equal with subintervals. And that's how it's going to be in this course when we do these by hand. But if we take it a step further and really focus on the most general sense, this is where we get the Riemann sum. With the Riemann sum, we don't have to make any specific concessions. The sum, we can use a capital S with a subscript P, the P meaning for partitioned sum, is going to equal the sum from k equals 1 to n of f c sub k delta x sub k. So what's happening is a couple different things. The first one is noticeable, is that we have this subscript k right here. That's because for the true Riemann sum, we don't have to assume this. All right, it's going to work no matter what we pick in terms of equaled width. Now again, for us, we're going to also, you can, every single time we're going to have equaled width in this course when we do these by hand, but the Riemann sum is saying it doesn't have to be. The other thing that you'll notice is you have the c sub k. Those c sub k's, which I have as x sub k's, those are going to be the arbitrary points in the subinterval that I said we'd get to here in a little bit. And so once we transition from this slide to the next, I can talk a little bit more about that. So that's the true Riemann sum. This is the whole idea of what we're doing. I'm going to now go ahead and clear the screen. We're going to focus on these c sub k's and these arbitrary points a little bit and tie a few more things together that we've talked about in the past.